Mark P. Otten back with you. All right, this is your measures of central tendency and variation in your data set. Descriptive statistics video. All right, to start, I'm just going to show you the formula for the mean. Well, I mean, you probably have seen this before. It's just you add all the scores up and divide by how many there are. Adding them up is denoted by this confusing, strange symbol. It's a sigma. It looks like a capital E. That's a Greek letter. That just means add them up. The X means the scores. That goes in the top part of the fraction. Then you divide by N, which is how many scores there are. The mean is denoted by X with a horizontal line over it. Okay, so I'm not going to test you on or require you to use the correct symbols here. I mean, you can just literally say sum, S-U-M, of O, F, X if you're typing this into your Excel document in your homework. Whatever works. And there's a separate video on how to calculate this stuff in Excel. So you can let Excel do the work. That's probably the best option. But anyway, this is how it's written in textbooks. I figured I should show you the conventional way to do it. And then at the bottom there is sort of the other version of this where you're just finding the sum. So the sum is equal to the mean times n, or how many scores there are. And that might be useful in your homework if I'm asking you, let's say I give you a mean and I'm giving you a total number of scores and then I'm asking you to get a sum, or maybe I'm like, hey, I just added one score to the sample. There's now 10 scores in the sample instead of 9, so n goes up from 9 to 10, and then you're trying to use the mean, which is given, to find the sum. Well, if you're looking at the homework, you know what I'm talking about. That formula at the bottom might be useful, and that's just like the same exact thing as the other formula. One is dividing, the other is multiplying. There's a little algebra trick that goes into making one of these formulas look like the other one. Don't really worry about it. I mean, I already got done filming a video telling you this is not a math class. I promise it's not a math class. So there's just the occasional trick here like this that can help you out. Just come to me, ask questions, we'll figure it out together. The median is the middle value of your data set. The key here is you just got to remember to put the values in order from low to high before you take the middle value. And if the total number of values is like 10, well, you got to take the average of the two middle values, because when there's an even number of total values, there are 2 in the middle. And so you just take the average of those. If there's an odd number, you just take the one that's in the middle once you put it in order. The mode is the most common value in your data set, and that's all I'm going to say about the mode. Okay, so between these, which one do you need to use like the most? It's pretty much the mean. That's always the case. Not always. Almost always the case in psychology research. Use the mean, but in certain cases the median is useful. For example, in this case, when you have a value in your data set that's like approximately 10 or 5 to 7 or something, you know about where it is, or you know where it should be in the order, but you don't know the number, the actual number. If you don't know the actual number, then, well, you can't calculate the mean, so the median is going to be the next best thing. Also, when you have an outlier, the median is useful. So an outlier, it's like when we have a bunch of temperature data, and there's an outlier here. In Northridge, it was a high of 47 degrees Fahrenheit the other day. That's an outlier. That's unusual. So then, if you have an outlier in there, or a few, and you take the median is less sensitive to that outlier. So that 47 degrees is pulling the mean down. It's dragging it down, whereas the median is, it doesn't really care. Like if you look at it, it's not going to care as much. The median is like, 47, it's at the bottom end. Let's just call it, it's a bottom, low value. Meh. I act like these statistics have personality. They don't really have personality. You calculate them. But when you calculate a median, it's not going to be as influenced by the outliers. Same thing with a positive outlier. If there's something at the high end, the median's not going to be as influenced as the mean is. So sometimes it might be useful to report the median, but you do it in addition to the mean typically, as opposed to instead of the mean. What about the mode? Well, sometimes you have nominal data or ordinal, like categories. So what's the mean of a Democrat and a Republican? What's the mean of a tennis player and a baseball player? What? Doesn't make sense. So sometimes you count up how many people are in those categories, and that count then becomes the data, and the mode is like the most common value. There's more baseball players than tennis players. That's a count. That's the mode. The mode would be baseball player. All right. So let's see about variation here. How much scores vary? How much scores are spread out in your data set? So like, let's say you have a bunch of temperature data from Northridge, and you have the 47, which is the low one, and then you have 115, which is the high one, and then you have everything in between. That's a lot of range, right? That's 47 to 115, quite a large range there. If you're only, let's say you're only taking data in August, well, you're not going to get a 47, like unless the world is falling apart and the ice age has arrived. You're not going to get a 47. You're going to only have like maybe 80 to 115 in August, right? So the range is smaller. And so if you're taking a standard deviation, it's going to be a smaller value. The standard deviation is actually the square root of the variance. So we talk about those, we talk about a variance, talk about a standard deviation. They sound very fancy. I'll show you in my other videos how to calculate them. But if you take the square root of the variance, you get the standard deviation. And the standard deviation is the mean squared deviation. Technically, sometimes it's called the mean square. And so what you do is you take these variations. Suppose your mean is 5 and your value is 7. The deviation is 7 minus 5. It's 2, and it's how far the value deviates from the mean, how far away that value is from the mean. So if your mean is 5, the value is 7, there's a difference of 2. And then you square that, you get a squared deviation. So like if it's 2, you square it, it's 4. Well, the math doesn't always work out so easily as in that example. But you square it, and then you take the average of all of those squared values. Again, I'll show you how to calculate this. But that's what this standard deviation is doing, and it's like a mean of those squared deviations that you take. And then like you divide by something, and then you take the square root. Again, I'll show this to you, but you divide by n minus 1. And so to get that mean, normally you would be like, oh, it's the mean of all of those squared deviations. So you divide by how many there are. That's what you do when you take a mean. Add a bunch of stuff up, divide by how many there are. That would be n. But here you have n minus 1. Oh, just to confuse you, why is it n minus 1? Well, in practice, you can just kind of do it. Just like if you're doing psychology research, let the computer do it. Put n minus 1 in there automatically. Don't question it. But we're here to question science. We're here to question why this is there and present a little bit of the background as to why this stuff is here. So it's a lingering question. Why do we take n minus 1 instead of n in the bottom part of the fraction? Well, this is a sample statistic. So we're typically in psychology, we're working with samples of data. People have filled out a survey. That's a sample of 12 people, let's say. So if it's 12 people, you subtract 1 on the bottom, you get 11. You divide by 11. And if it's a sample, you divide by 11. If it's a population, you actually would have divided by 12. So what's going on here? Well, in this example, suppose our sample standard deviation is 22. We're actually saying that the population standard deviation is 22 based on our estimate from the sample. So maybe we have a sample of CSUN students. That's our sample. And we're trying to apply our findings to a greater population of all university students everywhere. So the smaller CSUN sample results are then being applied to a bigger population, which is samples are usually subsets or taken smaller chunks of a population. So like in a sample, the standard deviation is typically going to be smaller, right? There's less people. So there's less variation. If we're just taking a few days in Northridge in that temperature example, just taking a few days, it's probably not going to be as much variation as if you took like a few years, right? So to account for this, we're making this adjustment and we're subtracting 1 in the bottom part of the fraction here. We're trying to make this adjustment and make the standard deviation bigger to translate it from a sample to a population. We're like, we know the population standard deviation is going to be bigger. We know that. So we're taking a sample and we're trying to make it a little bigger by subtracting 1. When you subtract 1 on the bottom part of a fraction, you're making the whole thing bigger because the bottom of the fraction gets smaller and the whole thing then gets bigger. If you're dividing by something smaller, the whole fraction gets bigger. So n minus 1 is the conventional way to go here. What they call it in the textbooks is an unbiased estimate of the population standard deviation. So once you subtract 1, it becomes unbiased. If you don't subtract 1, it is biased, and you are a terrible researcher. No, you've just made a small error. My question is why? Well, I have 2 questions. Number 1 is, why do we not subtract 2 or 1.3 or some other value? Why do we have to subtract 1 specifically? I don't know. It bothers me. It probably doesn't bother you. But if you're curious as well, let's have a conversation about that. Number 2 is, why do we have to square all the deviations? Why can't we just take the absolute value? You know, when you take absolute value, like the negatives become positive. Well, that's what happens when you square it. Why just take the absolute value and then take the mean of those? Well, on that topic, I actually wrote a paper when I was in grad school because I was a nerd, and I still am. But I wrote a paper on the absolute value method. It turns out people have studied this and rejected it for various reasons, but I still like it. And if you want to see that paper, or if you're curious and you're still watching this video and you're like, I'm a nerd, I want to figure out why this stuff is the way it is too. It doesn't make sense. I want it to make sense. Let me know. Send me an email. I can show you that paper. We can talk about n minus 1. Otherwise, just go back to the calculations. SPSS, these programs, they're just going to do it for you. So if you're not overly curious about the details and the origins here, just let the computer do it. It's cool.